Welcome, everyone. Thank you so much for coming. Welcome to the first of the meetings in this semester of the Initiative for the Sciences of the Past at Harvard. I'm Mike McCormick, and Chick has the privilege of chairing that. And I'm going to say nothing more before I turn this over to my friend and colleague, Noreen Ross, with whom I've had wonderful archaeological and molecular explorations in the fields of Flanders and in the mountains of Tbilisi. But before I do that, I want to simply say one word about radiocarbon dating, and that is, of course, that's something that is typically of great interest to people working on the very, very deep past. It's notorious that classical archaeologists never go near radiocarbon dating. We had an excavation in eastern France. It's been going on for 4 or 5 years. And when we took samples for radiocarbon dating, our colleagues were absolutely shocked. Why are you doing that? It's so expensive. And plus, you have pottery and you have coins, so it's perfectly dated. We did the radiocarbon dating, and of course it showed, well, it turns out that despite everyone's laughter and the expense, it turns out that the site was active about 50 years later than the latest coin. In other words, old coins were circulating on this late Roman site. So I think that even for classical archaeology, radiocarbon is a good thing. Noreen Ross is going to introduce our visitor, and we have a wonderful panel of commentators.
Hi. So, radiocarbon has been a tremendous boon to archaeology. J. Desmond Clark wrote, were it not for radiocarbon, quote, we would still be floundering in a sea of imprecisions, sometimes bred of inspired guesswork, but more often not imaginative speculation. Radiocarbon
At least it's imaginative.
the brainchild of Willard Libby's, why don't we name our children Willard anymore, who came out of the University of California at Berkeley, was then called California University, and toward the end of World War II, he took a full professorship at the University of Chicago. It was there the idea that radiocarbon might be incorporated into biota and decay at a regular rate and give us an absolute chronometer was developed. So it was Willard Libby's original idea, worked on by many people in the ensuing years. Many people now think of it as a sort of just a fee-for-service technique. Tonight, I'm really glad we're going to have an example of someone who's deep in the trenches, still doing research on radiocarbon, because as Libby said, quote, true, the initial ideas are in general those of an individual, but the establishment of the reality and truth is in general the work of more than one person. So let's welcome Dr. Michael D. has a PhD from the Oxford University. He's been at Oxford for a while as a Leverhulme Fellow as well as other positions, and is just moving to Göttingen to be in charge of isotope chronology. He will speak to us solar storms, tree rings, and astrochronology, new radiocarbon research from Oxford. Mike.
Thank you very much indeed. Is the microphone working? Good. There's about 5 parts to the talk I'm going to give today. First, I want to address the issue of measuring time as precisely and accurately as we can. Talk about what I think is the great breakthrough that's occurred in recent years by a lady called Fusa Miyake working at the University of Nagoya. And I go on a bit of a digression here into things to do with using radiocarbon as an astronomical technique, which I'm also working on. And then more concentrate on the application of what I'm calling Miyake events to dating things in the past exactly, to the exact year. And my new project from the European Union, from the ERC, called Exact Chronology of Early Societies, ECHOES. So starting with chronology, what I'm not going to talk about is probably the chronology that most people are familiar with, which is all essentially relative chronology. King lists, historical records, typological chronologies, ordering artifacts by type, and of course stratigraphy. These things, I think everybody knows, have the main limitation that they only ever order events in the past. They don't tell us anything about how long those events, how long those periods lasted, or when exactly in absolute time they occurred. So here's a fairly, in some ways, quite an oversimplistic example of why it's important that we concentrate on absolute chronology. At the top here we have the publication of the Communist Manifesto by Marx and Engels, actually in London in 1848. In the middle, the Russian Revolution in 1917, and at the bottom we have the Spanish Civil War. All three of these events in separate locations. If these dates were not common era dates, but BC, before common era dates, using current techniques or with our current knowledge, in truth, they would be indistinguishable in time. If this was 1848 BCE, we would not be able to tell whether the Communist Manifesto was a response to the uprisings in Russia and so on, or whether it inspired them. And this is why it's very, very important to get everything situated properly in absolute time. What people may not know is that the annual chronology of Eastern and Western civilization runs out in the first millennium BCE. It's kind of this asymptote there. The West is sort of hinges on this observation of a solar eclipse in the 9th year of the king Ashur-dan III in Assyria. From then on we have year-on-year records. In China we actually don't have records back as far as 841, but we have records from the grand historian of China called Sima Qian, who wrote in the 1st century BCE, and his records are so trusted in China today that, well, they stretch back as far as this particular time period, and it's thought that all of that coverage of the first millennium BC is right to the exact year. Now, a lot of you will know we obviously have chronologies that predate that particular point in time that stretch back off actually several thousand years back this way in Egypt and Mesopotamia and elsewhere. But again, these are piecemeal chronologies that what we call float. They're floating chronologies in absolute time. Nothing is fixed precisely. And so you end up with this, what I regard as a rather absurd situation where these are three current historical publications, really, where the historians are naming an accession date for Khufu, the Cheops, the builder of the Great Pyramid in Egypt. Here 2571, here 2509, and here 2593. In truth, they just don't know. Those dates differ by 90 years. How can we compare his reign with what was going on in Mesopotamia, what was going on in the Aegean, or elsewhere? When we talk about the history and the transference of ideas and technology, I can understand why historians want to adopt this convention, because these are events that took place on human timescales. They're years, they're actual events that occurred, and they're not nebulous probability density functions that I'm about to talk about with radiocarbon dating. But this still is, at its heart, it's false, it's wrong. How can we get to, using scientific dating techniques, actual years? Well, at the moment, the only real technique is dendrochronology. I'm sure that everybody knows that we have dendrochronological archives, tree ring archives, are made up of long-lived and fossil wood, dredged up from bogs and so on, where the ring patterns are matched. So you end up with very long sequences of tree rings within which you know exactly the year each of those tree rings grew, the calendar year they grew. So you're able to do amazing things like this Sweet Track, which is in the west of England. It's a causeway. And it's dated to the winter of 3808 to 3807 BCE, because they're able to match the ring patterns with the oak archives in that part of the world. But that in itself is kind of the limitation of dendrochronology. You need a big wooden sample with lots of tree rings for a match, and you need a solid, reliable archive, essentially in the same species, in the same region, for it to be appropriate or usable.
So you actually have that from the present past?
So I should have said, yes. So in Northwest Europe, we have an oak chronology, which goes back 14,000 years, in fact, and within which we know, in several places actually, in Germany and in Ireland and so on, we have tree rings we know the growth year of going back that far, the whole of the Holocene, in fact. Now, when we come to radiocarbon dating, why can't radiocarbon dating do that? Why can't we get such accurate results from radiocarbon? So what we do just briefly in radiocarbon is we make a measurement, a Gaussian estimate of what the isotope ratio is, essentially the ratio of radiocarbon in a sample to stable carbon. But then what we have to do is actually take this measurement and correct it, or as we say, calibrate it for the changes in radiocarbon concentration in the atmosphere going back through time. The concentration in radiocarbon in the atmosphere, which actually Libby didn't know whether it was going to be constant or not, it turns out actually De Vries was one of the first to discover it actually fluctuates back through time. So what we have to do is correct our dates, and we end up with this here, which is a probability density function across real time, across absolute time, within which it's true to say that this calendar year here, for example, is much more probable than these here. But what we prefer to say is that we have 95% confidence that this sample dates to somewhere in this area here. We don't want to pick out individual years. It could be anywhere within the sort of 95% range. And the problem is that you make a measurement, a typical measurement we might have made at Oxford, something like this. You compare it with this tree ring record, you correct it, and this is the date here. It's about 140 years in breadth, which is no use really on its own. So you try and double date, triplicate date. In fact, if you date that sample 10 times, you end up with something like this. But it's still, because it's bounced off this curve here, it's still a very broad 110 years or something there. So no matter how many times you date that sample, and as someone said already, it's $500 a date, you end up hitting what we call a plateau or a wiggle here in the curve, and you still can't get past that point. And until now, there's been no solution to this problem. So the pathway we took, really, at Oxford to try and deal with this was implementing something called Bayes' theorem and Bayesian mathematical modeling. And it's based around this theorem here. And essentially, all I need to say about this is that it gives us the chance, I can't see the whole lot there on the screen, but what it says is to combine absolute dating information, which is our radiocarbon date, in fact, with relative dating information, which is things like the ordering of events that we know from archaeology. For example, if we have 3 radiocarbon samples from a layered site, with the archaeologist tells us for sure that C is going to be older than B is going to be older than A. It has to be. No matter if these are the probability density functions and they sort of overlap and they stretch for 150, 200 years, C has to be older than B, has to be older than A. We can put this into the computer algorithm and calculate refined probabilities, and as you might imagine, it does something like this, where particularly the samples in the middle get squashed up and condensed and are more refined. And using that sort of approach, which we've applied to Egypt and various other places, but this is the work I did for my PhD some time ago, we knew the ordering of the kings in these different periods of Egypt. We loaded the model with lots and lots of radiocarbon dates. We also introduced other information we had about the approximate lengths of reigns of various kings of Egypt. And what it put out were these probability functions here, the grey ones. And first of all, they married up with the sort of red and blue markers, which represent historical estimates for when these kings acceded to the throne. In truth, if you didn't trust radiocarbon at all in Egypt, which at the time some people didn't, there's no reason why these grey estimates shouldn't be miles off this way or miles off that way. It just so happens that they marry up very well with what the historical estimates were. In fact, they follow this line which is called the high chronology, the sort of older dates for the estimates for these particular kings. And this was sort of as complicated and as sophisticated as a model as you could build, really, for something like this. And in the end, for some of these periods here in the New Kingdom, we were able to get radiocarbon estimates down to about 20 calendar years. But that's really unusual. There's not many other archaeological contexts where that would ever be the case. In fact, I then carried on this work, my first postdoc, and I essentially tried to extend back the Egyptian chronology to the first dynasty and got accession dates for these kings, which of course we didn't have because the historical records sort of begin after this. And what one's able to do, because they're mathematical functions, is just subtract one from the one before it and get estimates here in the right-hand panel of how long each of the kings was in power. And it was quite nice because, for example, we got sort of longer lengths of time for Jer than we did for some of these kings in the latter part of the First Dynasty. And then when we went to Abydos, where these kings are buried, you see the tomb of Jer, and it's absolutely enormous. And it's surrounded by 318 subsidiary burials, courtiers killed at the time of the king. Absolutely enormous thing. And the latter ones here are sort of ramshackle, smaller tombs and monuments. So one can imagine that perhaps Jer was a great and powerful and long-lived king, and the others were more sort of ephemeral. So the radiocarbon data married up very well with the archaeological data. But that's about where we are, or where we were with radiocarbon dating, with scientific dating until now. That was kind of the limit of it. And then Dr. Miyake published this paper in Nature in 2012, and an awful lot has happened since then. It's not long ago, really, but let me tell you what she did. So these are years here of the Common Era, and this grey line is the smooth calibration curve value of the concentrations, essentially, of radiocarbon in the atmosphere. Radiocarbon is produced by the bombardment of the Earth by particles from space. It costs $500 to do a date, so we didn't think that it was going to be worthwhile drilling down any lower than 10 yearly to have a record of what was happening in radiocarbon in the past. What people did at the time was they took blocks of 10 tree rings and they averaged what the radiocarbon value was there, and they went back through time like that. If you made sort of duplicate, triplicate dates on every single year, which would be a fantastic thing, but it would cost tens and tens of millions of pounds to do, it was just unaffordable. And we didn't think that the cosmic flux would vary very much from year to year. So we made a smooth curve. Fuse looked at this little sort of uplift here in the wiggle and thought, and then she looked at these raw data points that actually you don't normally see. They underlie this curve. Probably people at the time thought this was an outlier. And she said, well, what if this is actually real? And she went and measured each individual tree ring over this time period at very high precision. And what turned up was a spike in the concentration of radiocarbon in the atmosphere, which was very soon afterwards corroborated by work on dendro archives from Russia, from New Zealand actually, from North America, all sorts of places. In exactly that year, in 775 AD, the concentration of radiocarbon in the atmosphere shot up dramatically. Because we have the tree ring archives, all we need to do is count them, identify the tree ring, and we can see that it happened all in the same year, everywhere in the world. Without going into much detail about this, radiocarbon is formed by the particles smashing into the upper atmosphere. It's called cosmic ray spallation, and it releases a lot of neutrons in the upper atmosphere that are actually captured, usually by nitrogen, to form radiocarbon. There's no other way that so many neutrons could be liberated in the upper atmosphere and cause a radiocarbon spike like this before the nuclear age, actually before the nuclear bombs went off, when a similar effect occurred. So something had to happen. Either the cosmic ray spallation had to suddenly increase, we had to be bombarded by a whole lot of particles in this year, or, even sort of more dramatically, we were hit by an electromagnetic pulse, gamma rays of extremely high energy that struck the Earth and split atoms through the giant dipole resonance and released a lot of neutrons this way. So the astronomical community went mad on this and started looking at all different scenarios as to what might have caused this uplift in radiocarbon, this spike in radiation in this year. On the top left is a supernova remnant. If a supernova had exploded, a star had exploded in the Milky Way quite close to Earth, we would have been hit by a whole lot of gamma rays. This is an artist's impression of an active galactic nucleus. These are some of the most energetic phenomena in the universe. In fact, there are various other scenarios that were proposed that might have allowed a whole beam of gamma rays to strike the Earth at this moment in time. Things like the collision of two black holes, collision of two neutron stars. In fact, when I first took this idea to one of the top top astronomers at Oxford, he thought that the cause might be two neutron stars in our galaxy colliding and then the radiation hitting Earth. Another very interesting possibility was the idea that either a comet exploded in our atmosphere in that year and it was itself enriched in radiocarbon and just sort of delivered a lot of radiocarbon to the Earth. And there was even one that said that maybe a comet smashed into the sun and the sun let off a lot of material. So in the end, there was a lot of papers. In fact, I've got them here, I think. Quite a few of them were published in the years after Miyake's original discovery of the spike. The final possibility was the sun, which you might think was the first one to look at, but from a radiocarbon perspective, it actually was the least likely one. And so in the beginning, we didn't think the sun would be responsible at all. And the reason for that is that the particles that come from the sun, that strike the Earth, are generally too weak to induce the spallation and create the radiocarbon. They're not strong enough. Most of the spallation occurs from cosmic rays that come from further out in space, much higher energies. Now, if there's a great big solar storm, you do see a slight increase in radiocarbon. But what's interesting is that actually in the radiocarbon community, we're used to, when the sun is very active, actually what happens is the solar wind is stronger and the magnetic field lines around the Earth actually close over and get more dense. And what you see in the radiocarbon record is a dip in the production of radiocarbon because the magnetic field lines protect the Earth even better from the deep space, very high energetic cosmic rays. So we didn't think generally that the sun was capable of creating this effect. Here was one next piece of evidence. This is the largest solar storm that has occurred in modern times. It happened about 150 years ago in 1859. It's called the Carrington Event. It was so powerful that the aurora, which are associated with solar storms, geomagnetic storms, which you only normally see, I guess you see them in northern Canada, but you can see them in Iceland and Norway, these sorts of places. They were seen in Hawaii and in the Caribbean and so on. So presumably at latitudes like this, the whole sky was like blue and green during the Carrington Event. And this is the annual tree ring measurements we already have over this event. And there's just nothing. If you compare it with the Miyake event, there's just no spike. So when I first proposed this project, it was to investigate the cause of these events, and it just wasn't clear to us that the sun was responsible. My first paper on this was actually investigating historical supernovae. We made measurements of the concentration of radiocarbon in the atmosphere from known age tree rings over the top of supernova that we know have occurred in the past. Actually, one of them was a Star of Bethlehem. I decided to look at that and see if that was... but anyway, all of them were historical records. And as you can see, by and large, nothing really happens. This is the zero line here when the actual supernova occurred. And the concentration of radiocarbon year on year doesn't really change. Certainly nothing like a spike. So by now, the writing was kind of on the wall that it wasn't a supernova. What happened was that a paper got published, several papers got published, but this was kind of the clincher, to show that Dr. Miyake's original paper had overestimated the energy involved in the spikes, the energy needed to create the spikes, by about 3.5 times. In order to really understand how the amount of extra radiocarbon in your tree rings relates to the extra energy the Earth has been exposed to, you have to build one of these very complex Earth system models, really, to see how everything interacts and how much extra energy was required to create that effect. And Dr. Miyake's model had 4 boxes, where this one's got like 13 or 14, I think. And in the end, they were able to downgrade the energy into the range that might potentially just be possible from the sun in terms of an absolutely enormous solar storm. And then Dr. Miyake discovered another event in 994 of the Common Era, only 200 years actually after the earlier one she discovered. Not quite as pronounced as the 775 event, but certainly substructure, annual structure in the radiocarbon curve that we didn't know was there. Tie points, markers in time. One of the first well, as you can already see, one of the first major applications of this work is to astronomy. And now that it's kind of been decided that the sun is the real cause, people have been looking at what mechanism might have occurred that could allow the sun to eject so much energy and so many particles at the Earth. And there are these things called superflares, which have recently been observed on, well, they've been observed on various stars in deep space. But they've also, very recently, these papers here, it's been confirmed that stars the same size and spin rate and so on as our sun can potentially produce superflares. This is only just like in the last couple of years. This has been proven. Superflares are something like thousands of times bigger than anything we've seen in terms of a flare from the sun, maybe hundreds of thousands of times bigger. So you get quite dramatic reports, and this is not even in a dodgy sort of magazine. This is Science. And they say here, could the Earth be fried by a superflare from the sun? And the only thing I kind of disagree about, you can't read the writing here in the blurb, is that they say it's quite unlikely. Well, we've got these two marker points that Fuz has already found. We don't know what else is underlying the radiocarbon calibration curve over the last 10,000, 15,000 years. We really don't know at the moment how regular these things are and how massive they could potentially be.
Can I chuck in a question?
Go.
If we had a Miyake event, what would happen to the internet?
It would go down probably.
So would it go down and really be totally fried?
Okay, so if there's a really big solar storm, the first thing that go down are those satellites out in space. They get knocked down, single event upsets and so on. If a great big geomagnetic storm occurs, and you get ring currents in the ionosphere and this sort of thing, the satellite communication would go down, so cell phones would go down. The worst thing about that, of course, is that it would affect all communication and all the markets and so on would be affected. If the storm is big enough, you get currents induced in the metal wires and pipes and so on Earth, and you get substations blowing up and really lots of bad things happening. So it's a very serious, I don't know about the Earth being fried by a superflare, but certainly it would be a catastrophe for modern, and as we develop and become more and more dependent on these networks and communication systems, we become more vulnerable to something like avionics, planes as well, are flying higher and higher, I believe, as the newer planes. And, lots of, I shouldn't digress too much on this, but, the dose rates of radiation there get quite concerning. Anyway, so we're working on developing a project at Oxford, and I think various other labs in the world are working on this too, essentially using these natural archives of the world, tree rings, as measures of what was going on in the near-Earth environment back through time. Terrestrial radiation events and the emission of superflares, fairly forced acronym for trees, that we're working on at the moment at Oxford. But what I want to talk about today is what all this means for chronology and how we can use it as an exact chronological technique. Okay, so now I've moved to the Netherlands, I feel at liberty to use Van Gogh's work as a background to my slides. So if I just recap what's going on in a Miyake event, we have cosmic rays striking the Earth and the production of radiocarbon. A small proportion of it is taken up by the biosphere. In a Miyake event, heaps more is produced. And the plants are enriched, not just the wood and the trees and so on. Everything growing at that time gets a signal before it returns back to normal. But there's that one moment in time, that 1 year, maybe even that 1 month, when the Earth is flooded with radiocarbon. That's an overstatement, but relative to what it normally is, the environment is enriched massively in radiocarbon. So every growing thing inheres a lot more radiocarbon than it would normally have. That gets us past this problem that I showed earlier, where no matter how much you measure the sample, you've got this wiggle in the calibration curve. Well, now what you've got is a feature in the calibration curve here. It's a spike, and it's a vertical spike in 1 year. It happens because it's a corrective curve, the spike goes downwards. But anyway, the point is that we have a marker point in time. So all you need now is a sequence of samples that come from consecutive years, and if one of them overlies the spike, it will be enriched massively in radiocarbon, so you will know where the whole sequence goes. And these sorts of annual sequences are not as rare as you might imagine. Autumnal leaves in lake sequences every year, tree rings, obviously, perhaps grain from year-on-year collections. I hope, that we can get papyri from consecutive years of king's reigns. If one of those papyri shows a spike, then we'll know the exact year that it was written. And if it has, a cultural date on it as well, we'll be able to situate that particular part of the chronology exactly in time. Is all this dreamland? Can this actually happen? It already has. Obviously, we've been working on this for 3 or 4 years, but we seem to quite often get pipped by ETH in Switzerland. This is what they did. They dated this church at a place called Valmustier in Switzerland. They essentially just went through the beams in the church and they found the 775 spike. And then you just count the tree rings to the edge. And you know when all those bits of wood were cut down. They dated this church to exactly 786 of the Common Era using this method. Last year, 2015, it was taken up by the climatology people. I think probably most people know the importance of the ice cores from Greenland as paleoclimatic records. It had long been suspected that the VAV counting, the ice core chronologies associated with Greenland were out by a small amount. And what this paper shows is that they've got here the Miyake tree ring data and they show the spike. What they did was they looked through and they got measurements on the annual concentrations of beryllium-10, which is produced in almost the same way as radiocarbon in the upper atmosphere. And they saw a spike in beryllium-10, and this year here, and this year here, and there were other archives in this particular figure. And all of them showed a spike in beryllium-10, 7 years from the Miyake event. So what they did was they shifted the ice cores. They so trusted this data and it to be correct that they moved all the ice cores back 7 years. And what happened actually was that the evidence of volcanic eruptions, the sulfur spikes and so on, throughout the ice cores, all married up much better with historical events when they did that. Just last week, the ETH people published something that we were working on as well in Oxford. We had a bit of wood from inside the tephra, the ash that's erupted from volcanoes, such that the tree was killed by the volcano. This particular one, which is kind of called the Millennium eruption of a volcano on the border between North Korea and China called Changbaishan. It's also called Baitushan. And what we were polishing up the rings and we were making the measurements, because if you find the spike, 775 or the 994, you know that year, so you just need to count to when the tree was killed by the eruption. Well, they already did it. They found the 775. Just last week, this is actually a group from Cambridge, which was perhaps even more galling. But and Lucas at ETH, and they did this and they published. And the really neat thing about that is that it's not just dating the eruption of this event. What it is giving that tephra horizon an exact date. They even say late 946 of the Common Era. So now all across East Asia where you find this tephra, you know you're dealing with the latter part of 946 CE. It doesn't matter if it's an environmental record or an archaeological record or whatever. And there's any number of other tephras and so on to be worked on if we can find some more Miyake events back in time. So getting a bit fed up at this point, I published all the things I was going to do before I did them. I wrote this paper because I'd thought for quite a long time that all of this has real application in archaeology. We have long connected sequences in archaeology, just like ice cores, that are not situated in time. They float, like I showed before. So luckily I got this money from the ERC to start a great big project at Groningen on echoes, exact chronology of early societies. So the first part of it, of course, is the exact chronology of early societies of the New World. And this involves the Mesoamerican chronology, what's called the long count. So probably a lot of people here know better than I that the Mesoamericans kept a record of the days as they passed. So they had a day count, which stacked up and stretched in the end over perhaps 1,000 years. And the long count dates are on monuments and so on, wooden artifacts in some cases. But this long sequence, even though there's a sort of conventional way of correcting it and correlating it with Gregorian, with absolute time, it still floats around. It's still not certain exactly where it belongs. I'm certain that it overlaps 775 though. And I think if we can find a bit of wood that has a Mayan date, or a monument that has a Mayan date that had wood in it, then we can connect the Mayan long count exactly in time, or at least we can check, we can falsify the corrections being used at the moment. It is astonishing, I think, for a lot of people to learn that the only really fixed date in the Americas at the moment is 1492. Everything before that is still uncertain. Now, Professor Kennett has already worked on such monuments here, actually not this particular one, another one from a Mayan site, but in some cases you do get a wooden object that has a Mayan long count date on it. And other times, just like the church in Switzerland, you have a whole lot of wood in a monument, and if you can find the spike, you can hopefully work out when that wood was cut down and get a very good estimate for when that monument was finished and what the date, the Mayan long count date was relative to the Gregorian calendar. And the neat thing here too is that there's of course the important debate about climatic change and the downfall of civilization in the Maya lowlands. And rather ironically, we have a better record of the climate in Mesoamerica at this time than we do of the civilizations. Because we have, for example, this speleothem, published here by Professor Kennett, that has 6 monthly records of the oxygen isotopes, essentially 6 monthly records of the rainfall in the Yucatan area over the whole of the Maya collapse period. But we still have a floating historical chronology, so marrying up the two and making connections about when exactly the drought occurred and when exactly the knock-on effects were is not something we can yet do. But as I say, if we can fix the Mayan long count in time, then these are sorts of questions that we can begin to really address. The next part of the project I want to work on is echoes of the old world. And this is where I come back to this diagram, and we have the floating chronologies here. And what I'm really hoping to do is be able to pin down some of these long conjoint sequences, things like the Middle Kingdom in Egypt, where you have a 200-year connected sequence, contiguous chronology, but you don't know exactly where it goes in time. We have a lot of papyri from the Middle Kingdom, and I've radiocarbon dated a lot of them before too. I'd really love it if we could find, perhaps more so in the New Kingdom, something like a papyrus that has a spike in it from Ramses II and his 15th year, because then you can fix the whole of the New Kingdom of Egypt in time, and that affects all of the Eastern Mediterranean, the dates we have for that. And what's more is that once that date is fixed, it's true forever. The date will be 1326 BC, and that's what it will be. It's not an estimate that will be refined in time. We'll be able to pin things down properly so we can build on them in the future. How am I going to find more spikes in the calibration data? Here is some of the raw data underlying the calibration curve over 775. This is actually the individual data points split out into the different labs that made the measurements. And as I say, at the time they probably thought some of these ones were bad measurements, but you can almost see naturally with the eye that there's something going on there. And what Dr. Miyake really did was just confirm that something was happening there. So I'm hoping that if we look at all of the raw data underlying the calibration curve, and we apply a technique I'm just about to go into, we might be able to find them, hone our efforts to particular spots in time, and use the tree rings we have from those years to identify such spikes. There's got to be more of them. If two have been found quite close together, there's got to be lots across the Holocene. Well, not lots, some. And strange enough, the technique that we are going to use for this, well, I'm hoping to use it for this on my project, is also based on Bayes' theory. Much more complicated stuff to do with, it's called Gaussian process modeling. And this is, in this paper we offer a gentle introduction. I can tell you this is not a gentle introduction, but I tell you, an excellent paper by Stephen Roberts, who teaches robots to think at Oxford. And he uses this particular mathematical method, and I'll show you some of the bits from his paper. Very, very powerful data science. You have a cloud of data here on the top graph, and it actually comes from the Dow Jones Industrial Average across here in the 1970s. And what Professor Roberts and his team were able to do were apply these Gaussian process methods to this data and use certain covariance functions within the modeling, knowing that certain events happened at certain times. You could just tell the model to look for what they call change points. And what turned up was this sort of patterning. And so what they identified was something here, something happened on this day, and something happened on this day. And it turns out that was the Opec Oil Crisis, and that was the impeachment of President Nixon right there. And here's another example. You have essentially just a cloud, several clouds of data, and these are photometric measurements from a distant star, brightness measurements of a revolving star. And what they're able to do is say, okay, use the Gaussian process to find some patterning in this data, knowing that it is going to be periodic. And so what they're able to do was essentially join the dots and produce estimates for the period of rotation of that star. So it's a very powerful technique. It's like normal Bayesian analysis. You have certain priors, certain assumptions you make at the start, and you apply that to the data, and you come up with refined estimates that can be really informative. I think we have clouds of data underneath the calibration curve from measurements on wood. We have lots of measurements on the ice cores on beryllium and on chlorine-36, which is also cosmogenic. We'll have a whole lot of data. We can put it all together, and I'm going to employ a data scientist to do something like this to see if we can. If you've got a question, sorry. Nope, sorry.
I'm just wondering in what way that Gaussian process procedure is better than just the Fourier transform of the data.
It's a good question, and the latter one does include a Fourier transform analysis. I mean, whether or not I could explain that, or whether or not I'm even capable of explaining, I'm not sure. To me, this is really witchcraft when it gets to this level of complication. From what I understand, rudimentary methods are just not as successful. You can apply more information into the Gaussian process algorithm, and it's able to deal with more probabilities. And it just so happens that the estimates it produces outperform conventional methods. That's what the paper says. As to exactly why that is, I don't think I could answer that question. We wrote a rudimentary, I say we, my collaborator on this particular paper wrote a rudimentary Gaussian process through the basic data underlying the calibration curve, and luckily it picked up something happened in 774 going into 775, and it identified these other years here as possible change points in the data set. Now, we think we can use much, much more data, and Ben admits that this wasn't a very sophisticated Gaussian process. We could employ someone who's been working on this for a long time, who can use much more data and use much more refined techniques, and hopefully tell us, if you're going to try and find one of these events, get some tree rings from this year, and so on, and see if we can identify them. So the object of this all, really, is to try to fix these floating chronologies, extend this absolute chronology of civilization in both the West and the East back in time, so that we can look at the transfer of ideas and the transfer of technology back, so that we can write ancient history with a sort of precision that we write modern history. In fact, so we can write it scientifically for the first time. Thank you very much.
Us. And I'm going to ask Erwin Shapiro to go first, because I know you have...
Not for a half hour, I'm not going to talk that long.
Professor Shapiro is with us at Harvard.
Should I go up to the front with the mic?
Whatever you like.
I don't have to move. Well, first of all, I'd like to congratulate Michael D. for a super idea to pin down historical events. I thought that was really a brilliant idea, and I applaud it. I have some comments to make which are somewhat disconnected and maybe to a certain extent irrelevant, for which I apologize. But I wanted to say first that I did not understand why it was called a spike. To me, it's a step function. There's an increase in carbon-14, and that doesn't go away like the spike goes away. It stays there until gradually, of course, it falls off, but on timescales far longer than anything here, because the half-life of the radioactive carbon-14 is something like 5,700 years, so it's not going to fall off quickly. So why is it not called a step function rather than a spike?
Well, first of all, it falls away mostly because of the drawdown from the atmosphere. So what you get is the tail. It only goes for actually a couple of decades. It's not like the actual radioactive spike, the half-life of radiocarbon. It's not going to go over thousands of years, right? There's an uplift in the atmosphere, and that gets equilibrated, taken up by the plants, and the sort of that exponential function drops within a couple of decades. Now, why it's called a spike and not a step function is because that was the word I used at the beginning when I wrote the paper. You're right. I think I had in my mind the idea of sticking things down in terms of chronology, so I thought spike was a good word. I was always a little bit uneasy with it because it's not, like say, an up and down in a year, and then which would have been clearer. Actually, in the beginning, I think when we first discovered them, we thought they might come down more quickly, and it might be more of a spike. And there is quite a tail. But step function's not perfect either, really. It is a sudden uplift, and it's that I sometimes use the term wave front, really, that we detect, that first rise. That's the distinct marker. Yeah, fair point. It's not really a spike.
It just sounds better.
It's not an important point. I shouldn't even have made it.
No,
It
it's
was
fair.
on my mind.
Make a spike.
Then I wanted to comment on what's causing it.
Yes.
When you made a case for its being solar proton events that looks promising, but it's not all that clear in my understanding. And another possibility that has been put forward, which also has its problems, but has not been completely stamped out, are short duration gamma ray bursts. And there, if it were short duration gamma ray bursts, that would really be neat.
It would be brilliant.
And you might even contribute to astronomy by finding some of these spikes or step functions earlier on in time.
Can I respond to that one? So I first took this project to the Astronomy and Astrophysics panel at the ERC, and this was in 2015. And I said to them, the cause of these events is still moot. It's not clear. To us in radiocarbon, am I being still recorded? I feel a little bit okay, we can hear this. So I'm not even.
Right, I'm also being recorded.
No, it's just like I don't because. And I said to them that what we can do is try and work out with better study of the energy and of the energy spectrum, what is actually causing these things, because it made more sense to me that it was a gamma ray strike. And I had a massive argument with a guy. There was 25 professors of astronomy in the room, and I knew the subject very well. And he was going at me about the fact that it was already decided it was the sun. And in the end, I didn't get the money through that panel, which is why I went to the archaeology panel then. But actually, that it could be a momentary failure of the magnetic field of the sun itself, which has then allowed the Earth's magnetic field to sort of open and relax right out, and then we get hit by a whole lot of cosmic radiation from space. And then somehow or other the sun's magnetic field restarts. Something very short like that. to him it's much more logical that it would be that than a massive solar flare. But I agree entirely that the matter's not dead, but it's a sore point for me because I lost my grant on that basis, that they said that it was matter decided, so I shouldn't pursue this anymore. But I agree that who knows what will really come of this until it's really, until there's more research done on that matter.
What you need are more events.
We do more, yeah.
And what I was wondering in that regard, and this is probably stupid, but you have these measurements, and they have fairly big error bars relative to the spike or the step function.
Yeah.
And I was wondering, is there any research going on to understand these error bars and understanding what goes into the fluctuations such that one can model them better and see smaller events, which would then be a significant contribution?
Yes. So the other real step forward we made, I guess, in the field in recent years has been an improvement in the particle accelerators we use. And they are routinely more precise than they were before. And so now, luckily with my move to Holland as well, we have a brand new machine coming, which is about twice as precise as the one we had at Oxford. So when we do triplicate measurements on that machine, we will be able to look at much smaller variations in the concentration of radiocarbon in the atmosphere. As it turns out, in the end, like the big spike, the big step function in 775 is still 7 standard deviations away from normal fluctuation. So it's like pronounced, it's there, it's not disguised at all by the measurement precision. But this generation of accelerators that are being produced now that everybody's starting to use are much more precise. And ultimately what I think we'll be able to do is look for just little variations in the curve. They may not be big jumps. They might be just an up and a down, but it's a distinct moment in time, which then we might be able to match that with an archaeological artifact and do the same thing. So it may not just be a hunt for real rises like this. We are improving the precision of the instruments, but ultimately it's down to counting statistics. So you have this sort of limitation that is kind of held us back. But you're right, this is another sort of frontier of research. It is an ongoing frontier.
One comment just based on that. Sorry
Yes.
to jump in, but the radiocarbon calibration curve, extends back with dendrochronology to about 14,000 years. So that's a lot of measurements to actually come up with that calibration curve itself. It started with traditional radiocarbon labs, not with accelerator mass spectrometry. So there were radiocarbon. So there were limitations on the sample size itself. So that's why they were measuring 10 years, because they needed that much sample to actually make the measurement. Now the labs, like at Groningen, I'll plug our new lab at Penn State, are measuring much smaller samples, so we can actually look at these events in much greater detail. So it's a technological revolution that allows us to look at this in greater detail.
And the other side of that coin is better modeling of what's going on and knowing what's causing these fluctuations. I was wondering if there's
There is, and
research
of
going
course
on
the concentration of
in that area.
radiocarbon in the atmosphere is very much tied in with global carbon cycle and modeling and the climate and so on. It's incredibly complicated because you get take up by the vegetation and transfer back to the atmosphere, and you get the oceanic release of dead carbon, volcanic events. It is a real mix. The neat thing about this is that it's a sudden rise in radiocarbon, which can only be caused by a big radiation burst. Except the nuclear bombs in recent times, they can do it too. But before that, it can't be anything else. More declines, which tend to be a bit more gradual, could be caused by any number of different things. But there is, this is a whole field of research too on the concentration of radiocarbon in the atmosphere and how it models and how it reflects generally the pathways of carbon through the carbon cycle and so on. Yeah.
The only other comments I wanted to make were, oh, there it is, up on the board. I didn't even ask for it. You have on the right dates, unfortunately I can't see it well from here, which say where there's a jump in the C14. And I've put question marks there because there are jumps on one side and decreases on the other. And on two of them, I remember, I couldn't see anything going on at all. And I didn't know, and sometimes I thought it was the reverse. And I was wondering how much reliability. I know there were caveats in the paper about these not being reliable yet, but premature.
But what you might-
they were put there, and I found I couldn't connect at all with them.
No, and I think that's their comment, but actually what's even more impressive is that, so yeah, what Ben was able to do was identify the sort of rises here and signals that looked like there were quite sudden drops there. But actually, honestly, sometimes the model tells you that there's something has happened here, and you look at the raw data and you can't see anything. And that's just the way it is. And actually, sometimes it's true. Like with the analysis of the stock market and so on. You look across the data and you can't see anything, and they say something happened here, and then you go back to the economics of it and you find out something did happen there. This process is very sophisticated, and it sometimes finds stuff in the data you didn't know were there. They could be just false positives, they could be just failures, or they picked up something that's not there. But often the model tells you something had to happen in the data at this point in time for the rest of the pattern to be consistent. And even though in that part of the data set you can't see anything, that's where you have to investigate. You have to trust the technique and investigate that area.
Okay, I'll let that go. Let me now end with just a wish that you have an excellent career ahead of you and that your job in Groningen works out to your
Thanks very much.
expectations.
Yeah, thank you.
Could we hear from Doug Kennett now, Chair of Anthropology at Penn State University and the owner of a new mass spectrometer?
Okay, well, first of all, thanks so much to Noreen for inviting me, and to Lisa for organizing my travel here today. All went very smoothly, and to Michael for giving a great talk. And I'll give sort of the Americas perspective as an archaeologist.
The Americans?
The Americas, yeah, I work in the Americas, so in the New World. On this, I think someone's going to talk about the Old World. So, first of all, just this is probably one of the most exciting things that's happened in radiocarbon calibration in my career, in 20 years. There's been sort of incremental improvements to the calibration curve, filling it, extending it back in time. Probably in the last 5 or 6 years, filling in an interval called the Younger Dryas, which was sort of a gap in the calibration curve. But in the last 5-6 years, it's been sort of, that's the calibration curve. We're stuck with it, as Michael said. It's not all grim through the calibration curve. And I think Michael used a certain example where there are plateaus in the calibration curve, and then there are cliffs in the calibration curve. So if your material actually falls in one of those cliffs, you can actually get greater precision than, say, 120, 130 years. But it's variable through the last 13, 14,000 years. So this is where I see this technique actually really helping within these plateaus. It turns out that almost everything that's interesting in prehistory
It's true.
happens within a plateau. Okay, as a Mesoamericanist, in the formative period, there's something called the Hallstatt Plateau. There's all sorts of interesting things that are happening around the world during that interval of time. If we don't actually have identified one of these during that interval, but it would greatly help to give us a datum. And this is what a critical element of this talk is. We're talking about a global datum. So like in geochronology, in stratigraphic sections, we often look for tephras that are a known age, and those help us figure out the stratigraphic sequence and determine their actual age. This is actually a global datum, and we have 2 of them now, which actually occur during an interval of time that I care greatly about, with the development of and collapse of Maya polities. Also in North America, I've also become greatly involved with work in the American Southwest, in Chaco, You'll see in the news in the next week or so, I can't say anything because I'm being videotaped, that I've been heavily involved with trying to develop chronologies in the American Southwest in Chaco Canyon. And in the Southwest, almost the entire prehistoric record is based on dendrochronology. In fact, I would actually call it an over-reliance on dendrochronology and on building sequences. And they haven't used radiocarbon. And they're missing things because of that. I also think in the dendrochronological world, and why this is significant, is that there's sort of there's error in dendrochronological sequences as well. And there's sort of an
Reliance.
not a reliance, but an over, they feel more, very comfortable with their chronologies. So I think having these events and going in great detail in the American Southwest and looking for these events and just verifying that their chronologies are spot on. And I think similar to the ice core chronology that you mentioned, I think there are going to be some shiftings of the chronology. They're going to have real significance relative to our understanding of the socio-political dynamics that are in play, relative to environmental changes and climatic changes, which I'm particularly interested in. So that's sort of some general comments. Are my slides on here?
I'll put them up there.
Okay. I'll just talk quickly about the Maya case, just a little bit more. Michael mentioned 2 papers that were published related to this, and again, just a couple of examples as to why this is potentially significant in the Maya region, and the way that, in a way, the way that I've used rudimentary techniques to try to address the correlation problem, which has been a long-standing problem in Maya archaeology. You have this floating Maya long count chronology, and then you have our Gregorian calendar, and we want to know how those two correlate. It turns out this is actually an ETH project, by the way. This project came out of ETH. And this panel is actually at a small museum. This is a wooden lintel, carved lintel with Maya hieroglyphic writing on it, with a long count date that represents the dedication date of this monument. So this drew a lot of interest by the radiocarbon community when radiocarbon dating was developed. Here's Willard Libby. We've been talking about him. In fact, I went and photographed and looked at this material. I was hoping to sample this material eventually. These are these thin panels. The lintels were actually thinned down. They were transported out of the Maya region and to this small museum in Basel, Switzerland in the 1800s. It's actually a pretty amazing story by a guy named Bernoulli. When the radiocarbon technique was developed, Libby wanted to date things that, he wanted to work on this correlation problem. It was sort of an open question. How does the Maya calendar fit with the Gregorian calendar? And that's actually his sample mark right there. So he went to Basel and he actually collected a sample and tried to come up with a tie point using radiocarbon between the Maya calendar with this particular long count date and an actual date in the Gregorian calendar. In fact, he got it wrong in terms of the measurement error was quite large at that time, and he basically pointed to one of 40. There are about 40 different proposed correlations based on historical records, and he pointed to one that turned out to be not correct. So this is a problem that I've been working on using some material from Tikal. These wooden lintels, basically, you can see just up here. They're basically ceiling panels that are beautifully carved, often with texts about wars. This is the panel that we worked on from Temple 1. And we were unable to convince the museum at Basel to sample their beautifully carved lintels. So we actually went to the University of Pennsylvania, where they had done some excavations on these same temples, and we were able to actually get the butt ends where Bernoulli had cut the lintels out of the temples back in the 1800s. And these actually turned out to be much better because we had the incremental growth in these beams to work with. One of the unfortunate things about trees in the tropics in general is they don't really have tree rings. And they don't have annual growth increments that are measurable. So there's no dendrochronological sequence for the Maya region. So we had to get kind of creative about how to look at this with the new technologies that we've been talking about. So using higher precision accelerator mass spectrometry, radiocarbon dating. So one thing that we did was we used multiple dates through the growth of the tree. I think you can see the radiocarbon dates here. Here are the ETH numbers. So I was doing a sabbatical there, and that's why I was able to go over to Basel and see the material. So this is the exterior growth fairly close to when the panel was carved. So this is where, this is the date that really matters in terms of the correlation. But we wanted to get incremental dates because we wanted to capitalize on the wiggles in the calibration curve. So if we could determine what the growth rates were here and come up with an estimate of the actual years represented in this piece of wood, then we could actually take the radiocarbon dates and then wiggle match them to the calibration curve. And these are actually approaches that were developed at Oxford for dealing with this statistically. Because there were no tree rings, we had to we wanted to know sort of how fast this thing was growing. And I think this is actually going to help Michael in the long run try to identify these events in these lintels, because there's really no dendrochronological roadmap to do so. So these are the distributions of the 4 dates that we did incrementally, and then we used laser ablation ICP-MS and basically ablated a continuous line across the lintel, and we basically were able to detect changes in calcium concentrations that appeared to be annual concentrations. And then we used that to come up with growth estimates for this particular lintel, which is they grow fairly slowly, so they're growing about maybe 1.5 millimeters per year. Okay.
At the ablation data, they've been tuned to something, right? That's not the raw.
Yeah, to carbon. Yeah. So based on that information, we've determined that piece of wood grew over about a 150-year interval. We used that information to wiggle match to the calibration curve, and then we compared the exterior radiocarbon date to the best known correlation that are out there, and confirmed the what's called the Goodman-Martinez-Thompson correlation to the best of our abilities. Now, unfortunately, you'll see that this occurs just before one of his known events. Okay? But it would have been really nice if we would have had one of those events in here. Would have created a datum that would have helped us with the growth rates, really trying to figure out the chronology of this particular beam, and therefore wiggle match it and really come up with a much more precise age for the correlation.
Doug?
Because I'll say there are actually different variants of this GMT.
Oh, yeah.
Yeah, that come down to days
Right.
and specific years. So there's potentially more work to be done. And I'd always say in this paper is our data is consistent with the GMT.
Mm-hmm.
I'm not completely convinced myself. I think more work needs to be done, but I became very concerned about that because of the other paper that Michael mentioned, which is trying to correlate specific events that are based on long count dates. So these are dated stone monuments and the frequency of them through time. But this is assuming the GMT correlation. These are warfare events that occur within here. So we're trying to look at the frequency of war in the Maya region relative to this very high precision climatic record that we developed for the area. But this is based on the Gregorian calendar. If the correlation is incorrect, then we're not really testing anything about the relationship between climate change and environmental change and potentially increases in warfare or decreases in the area. So that's why when I was working on this paper is when I started becoming worried about the GMT, and that's why I ended up doing the study in Switzerland with ETH to try, to at least check on the GMT to see if it was correct. What you'll see here that I think is important is that there are events, much of the classic actually occurs before this first Miyake event. But there are some monuments that have long count dates that go beyond this time. Some of these may be wooden artifacts. Most of these are stone monuments, but there are some wooden artifacts that could extend out here. And there's certainly lintels that date to this time. I'm not sure if there are lintels that actually have long count dates carved on them. But there looks like there's some potential at Temple 3 at Tikal. So.
Thank you. Could I ask you a question?
Yeah.
The Mayans had written language, right?
Yeah, that's, yes.
So, and they must have been very impressed with the total solar eclipse. Didn't they write down in their records when there was a total solar eclipse? Then we can pin down to the minute or better the connection between the Gregorian calendar and the Mayan calendar.
Professor Fash.
Well, Professor Fash probably wants to go into that. Sorry? Professor Fash, that's his area of expertise. Yeah.
I'm not an epigrapher, but I know enough to say that there are records of solar eclipses and lunar eclipses as well, but they're in books that date to 500 years later that don't have long count dates. This is the problem. They only have short count dates. And in terms of a wooden lintel, that would also have the spike and a reference to a solar eclipse that we do not have.
These kinds of histories are very specific, so they're often related to elite individuals. You can see this king seated here, and this text is about this individual, and it's usually related to their accession, their any kind of triumphs in warfare, very specific kinds of marriages, but not detailed text like in the post-classic books.
Also,
and there are only 4 of those books.
Another part of the reason why classic Maya king wouldn't have recorded a solar eclipse in his own personal histories, they were thought to be very unlucky events. They were afraid it could be the end of the world. People would go out and howl and break all their pots and pans at night when these things would happen. So you wouldn't want to record that happened in your reign.
So, if I can ask last, but by no means least, Assistant Professor Tryon from the Department of Anthropology to give us the deep time perspective.
The short perspective. I'll do it as quick as I can so people have time to ask questions as well. I have no slides, and everything can be recorded going forward. First, thank you, Mike, for an excellent talk. Thank you, Mike McCormick and Noreen Gross for the invitation to say a few things. I really appreciate it. I was glad to start with a quote from Desmond Clark. That's my intellectual grandfather, so I was sort of surprised to hear the start with his thinking about the radiocarbon record and deep time. What struck me most about this, in thinking about calibration, radiocarbon dates, we normally think about making our dates a bit more precise, but for me, it's also what this talk did is it makes us think a little bit about calibrating how we sort of think about the past, and so that I work in deep time. I work in the Paleolithic record, and it's only in the last few years I've even worked on sites that are within the radiocarbon range, right? So for things that are 30, 40,000 years old, the dates are plus or minus 500 or 1,000 years. Now, these are tens or hundreds of human generations, and so you don't ask questions that are sort of specific. You ask these sort of broad stroke questions. Yes, you try to find sort of global events that might serve as tide points. You could have things I work on like volcanic ashes that are sort of floating, sort of local, or you might get changes in the Earth's the geomagnetic polarity, but even those, we don't know how long those happened. And those dates change every 5 or 10 years, and plus or minus a few thousand years. So having things like these Miyake events are really exciting because they do give you this sort of global timeline. And I think as archaeologists, I think the ultimate maybe dream of an archaeologist, at least for me, is to do a true, truly sort of comparative anthropology. You want to be able to say, okay, at this point in time, what's going on in the world, and how is it different, and how is it the same? And I think for most of us who try that, you know that you're mixing sort of space and time variability together. These things really sort of give me hope, at least, that we can sort of push back, asking these really fine-scale questions. And what it means is that the sort of historic record or the last few thousand years are going to be a really neat sort of laboratory to see what works and doesn't work for the Paleolithic record. So I thought this was really sort of exciting talk, and I thank you for it.
Thanks. Can I just say to that, one thing that I wrote in my proposal, which always makes me realize how profound all this is that when they discovered the spike in the church in Switzerland and were able to date it that way, in fact, every wooden building in the world, in Japan or everything else that was built at that time will have that spike. So it unites every structure, every wooden thing that was made at exactly that time will have that event. And it really is a global linking mechanism. Yeah.
Thank you. If you want to stay and ask questions, you're quite welcome. But are there any questions right now?
You asked all of them.
I do have a question actually about difference between the hemispheres, northern and southern hemisphere. I mean, we're talking about a global event, but the carbon cycling happens in different ways.
It's a good question. So basically, the concentration of radiocarbon in the atmosphere in the southern hemisphere is slightly different from the northern hemisphere. They track pretty similar sort of patternings, but this one's what we call 40 radiocarbon years below this one. When the event happens, you get the same spike in the same year. It's actually that this one is set downwards from this one in terms of absolute measurement, but actually they rise almost exactly the same amount and they fall back down. The concentration of radiocarbon in the atmosphere in the south is lower because we think there's much more deposition, essentially, of radiocarbon into the oceans. There's much more ocean in the southern hemisphere. So everything's a bit lower down the scale, but the events still are exactly the same time and kind of the same magnitude as well. Yeah.
So I think I've got a pretty good grasp on what your talk was about. My understanding of the Miyake events is the way you're able to identify them is you can count through Dendrochronology, get the specific date, and then with AMS you get such a small sample you can you can AMS that and see that there's the spike or the step plateau. I'm just thinking of an example. I work in Southwest United States. What if I say I have a site that's dated from, I know the range to be 700 to 800 AD. Mm-hmm. I don't have any tree rings though, but I get some annuals dated through AMS.
Yeah.
If just by chance and coincidence one of those annuals comes from 774, would that show up as having, would you be able to see that, I guess?
So firstly, it will happen, and it will date sort of away from the others around it, as it were. The problem is that you need a little sequence because you don't know if it's just not an intrusive sample from a younger period that has an enriched concentration of radiocarbon. Even though the rise is quite distinct as you track from year to year, I mean, if you pick it up, for example, we had a papyrus one time that I worked on from the British Museum, and it had a concentration of radiocarbon that was much higher than we, thought it should have, and it was about 100 years or whatever too young, which is actually, when you do the math on this, is about a Miyake event sort of amount of radiocarbon extra it got. In the end, you're left with a problem you can't solve, really, because the people in the museum were absolutely certain it was original and it dated to this time period. My measurements show it's down here. Unless you can put it in a sequence and know, like I say, if it's King's years 1 and 2 and 3, and you know it's in a sequence and you can see the spike happen, you can't really know, I don't think, whether it does date to a spike or whether it's something from a later time period that looks like it's from an earlier time period. And it's too isolated as a data point, I think. Though I'm thinking about this a lot myself, and like you say, if you have a whole bunch of grain and you measure a whole lot of them, and some of them show a spike, does that mean that collection of grain overlies a Miyake? Probably, I would think, but it starts to get a bit more difficult to sort of argue at that point.
Yes, very quick math on the figures that your collaborator did. I think just those 6 dates based on the Gaussian estimates, and it looked like the intervals were 600, 700 years, 600 years, 1,000 years.
Yeah.
Now, is that what you actually think the frequency of the Miyake events are going to be, or is that, or are they likely to be more common than that, simply because of the way in which this particular sample was done?
Again, well, two things. One, I think that the model we've run, we don't know yet whether it's any good, really. It may not be that those results are really reliable. When we do much better models, we'll see if there's any pattern to them. Again, this is all connected with the cause of these events. One thing that's quite exciting is that if you take the 775 event, then the 994 event, and then 220 years later, and 220 years later, 220 years later, you hit the Carrington Event of 1859, the largest solar storm in modern times. So it might just be that there's some cycle that's being exposed here. I probably shouldn't be recorded on video saying this too, because this might not actually be true at all, but it could be that there is a pattern to it. Again, we don't see anything at the Carrington Event, so it might be that it does happen every 200 years, but we only see every 600 years. Maybe there's a large, we just don't know what the patterning is yet, I think is probably the answer to the question, or whether there is any patterning. But it just seems to me, if we've only done a certain number of tree rings, and they've only really been done by the Japanese group in the late first millennium, and they've found 2, history is about 5,000 or 6,000 years breadth now. There's got to be more out there we can use, even if it's just 1 or 2 more that we can use. I don't think I can really say anything, despite what I've just said, about the patterning on them just yet, really.
Thank you.
But, thank you. Thank you. Thank you.